Between Mars and Jupiter lies one of the most misunderstood regions of the solar system, the asteroid belt. In movies, it is often shown as a deadly obstacle course packed with tumbling rocks, where a spacecraft has to dodge boulders every few seconds. The real asteroid belt is very different. It is a huge, ring-shaped region around the Sun, filled with countless rocky and metallic bodies, but spread across such an enormous volume of space that most of it is emptiness. On average, asteroid belt objects are separated by around 1 million kilometers. That means if you were floating beside one asteroid, the next one might be farther away than the distance from Earth to the Moon several times over. The belt is not a wall of rocks. It is more like a vast, thinly populated archive of ancient solar system material. The asteroid belt is often called the main belt, because it is not the only place in the solar system where small rocky or icy bodies exist. There are near-Earth asteroids that cross close to our planet, centaurs that orbit among the giant planets, distant Kuiper belt objects beyond Neptune, and even more remote populations in the scattered disk and Oort cloud. But the main asteroid belt is special because it sits in the inner solar system, roughly between the orbit of Mars and the orbit of Jupiter. It is the smallest and innermost circumstellar disk around the Sun. Even though it contains millions of objects, its total mass is surprisingly low. If you gathered the entire asteroid belt together, it would add up to only about 3% of the Moon's mass. That low mass is one of the keys to understanding the asteroid belt. It is not the remains of a full planet that exploded, even though that idea became popular in older science fiction. Instead, the asteroid belt is more like a construction site that never finished building. Early in the solar system's history, the region contained many planetesimals, small solid bodies that formed from dust and rock in the primordial solar nebula. In other parts of the solar system, planetesimals collided, stuck together, and gradually built planets. But in the asteroid belt, that process was interrupted. Instead of calmly merging into one larger world, many bodies were stirred into faster, more violent orbits. Collisions became destructive rather than constructive, breaking objects apart instead of allowing them to grow. The main reason the asteroid belt never became a planet is gravity, especially the gravity of Jupiter. Jupiter is enormous compared with every other planet, and its gravitational influence reaches far across the solar system. As the young solar system evolved, Jupiter disturbed the orbits of objects between itself and Mars. These gravitational perturbations gave planetesimals extra kinetic energy, making their encounters faster and more chaotic. Mars also contributed to disturbing the region, but Jupiter was the dominant sculptor. When small bodies collide slowly, they can merge. When they collide too fast, they shatter. Over time, the belt lost almost all of its original material. Scientists estimate that about 99.9% of the asteroid belt's original mass disappeared within the first 100 million years of solar system history. The objects that remain are not all the same. Some are dark and carbon-rich, known as C-type asteroids. These are among the most common and may preserve primitive material from the early solar system. Others are S-type asteroids, made largely of silicate minerals and often brighter than carbonaceous bodies. Then there are M-type asteroids, which are richer in metals such as nickel and iron. These categories come from the way asteroid surfaces reflect light, giving scientists clues about their composition. In a sense, the asteroid belt is not just a collection of rocks, it is a mixed library of planetary ingredients. Some asteroids resemble leftover building blocks. Others may be fragments of larger bodies that once heated, separated into layers, and were later smashed apart. A few asteroids dominate the belt by size and mass. The largest is Ceres, about 950 kilometers across, and it is the only object in the asteroid belt classified as a dwarf planet. Ceres is large enough for its own gravity to pull it into a rounded shape, which sets it apart from the irregular rocks around it. Then there are Vesta, Pallas, and Hygiea, each smaller than Ceres but still massive compared with most belt objects. Together, Ceres, Vesta, Pallas, and Hygiea contain around 60% of the asteroid belt's total mass. That means most asteroids are tiny by comparison, ranging from hundreds of kilometers across down to objects only a few meters wide. The belt sounds crowded, but most of its matter is locked inside a small number of large bodies. Ceres is especially important because it blurs the line between asteroid and small world. It is not just a random rock. It has a rounded shape, complex surface features, and evidence that water-bearing minerals exist there. That makes it valuable for understanding how water and other volatile materials were distributed in the early solar system. Vesta is also fascinating, but for a different reason. It appears to have experienced internal heating and differentiation, meaning its materials separated into layers, almost like a miniature planet. Meteorites found on Earth have been linked to Vesta, giving scientists actual samples from one of the asteroid belt's largest objects. These bodies show that the belt is not uniform debris. It contains worlds with very different histories. Even though spacecraft have passed through the asteroid belt many times, they have done so without dramatic collisions. Pioneer, Voyager, Galileo, Cassini, New Horizons, and other missions have crossed the region safely. That is because the distances between objects are enormous. The danger is not that a spacecraft will randomly hit an asteroid every few minutes. The challenge is finding and reaching a specific asteroid at all. Mission planners need precise trajectories because the targets are small and separated by huge gaps. This reality changes how we should imagine the belt. It is not a dense storm of rocks. It is a nearly empty region containing scattered islands of ancient material, each moving around the Sun in its own orbit. Collisions do still happen, but not in the constant cinematic way people imagine. Over long timescales, asteroid impacts can break larger bodies apart and create asteroid families. Members of an asteroid family share similar orbital paths and often similar compositions, suggesting they came from the same parent body. By studying these families, astronomers can reconstruct impact events that occurred millions or even billions of years ago. It is like forensic science on a solar system scale. A shattered asteroid leaves behind fragments that continue orbiting the Sun, carrying clues about the original object. Some of those fragments can later drift into new orbits, eventually becoming meteorites that fall to Earth and deliver pieces of the asteroid belt directly to our planet. Jupiter continues to shape the asteroid belt today through orbital resonances. A resonance happens when an asteroid's orbital period forms a simple repeating ratio with Jupiter's orbit. For example, an asteroid might complete 3 trips around the Sun in the same time Jupiter completes 1. Each repeated gravitational tug may seem small, but over many orbits the effect builds. These resonances can push asteroids into more eccentric or unstable paths, clearing out certain regions of the belt. The result is a pattern called Kirkwood gaps, named after astronomer Daniel Kirkwood, who noticed that asteroids were missing from specific orbital distances. These gaps are not empty by accident. They are gravitational fingerprints left by Jupiter's long-term influence. Those unstable paths matter because some asteroid fragments eventually escape the belt and move inward toward the terrestrial planets. This is one way the asteroid belt connects directly to Earth. Many meteorites that reach our planet began as fragments of asteroid belt bodies. Over time, collisions, sunlight effects, and gravitational resonances can shift small objects into orbits that cross Mars, Earth, or other inner planets. Most burn up in the atmosphere as meteors, but some survive to reach the ground. When scientists study meteorites, they are studying pieces of ancient planetary material. These samples help reveal what the early solar system was made of before planets fully formed, melted, and chemically changed their surfaces. The asteroid belt may look like a region of leftovers, but leftovers can be scientifically priceless. Planets are active places. Their interiors heat up, their surfaces change, their atmospheres react, and geological processes erase early evidence. Many asteroids, especially smaller and more primitive ones, preserve material closer to the solar system's original ingredients. They help answer questions about how dust became rocks, how rocks became planetesimals, and why some planetesimals became planets while others remained small. The asteroid belt also reminds us that planet formation was not a neat, guaranteed process. It depended on location, timing, collisions, and gravitational influence. Between Mars and Jupiter, the ingredients for a planet were present, but the environment was too chaotic for one to survive. So the asteroid belt is not a cosmic junkyard, and it is not the wreckage of one exploded planet. It is a preserved record of a failed planetary assembly line, shaped by Jupiter, thinned by ancient collisions, and still slowly changing today. Its largest members, like Ceres and Vesta, show hints of what small worlds can become. Its smallest fragments can eventually fall to Earth as meteorites. Its gaps reveal invisible gravitational patterns written across space. And its emptiness is just as important as its rocks, because it shows how enormous the solar system really is. The asteroid belt is a reminder that sometimes the most interesting story is not about the planet that formed, but about the planet that never did. If you found this helpful, please like this video and subscribe for more explainers.